When an object sustains an impact, the energy does not teleport to the other side. It travels through the material as a wave. We often refer to the speed of sound as if it were a single fixed number. In reality, it is a highly dynamic property. The identical physical mechanism produces radically different propagation speeds, depending entirely on the environment it moves through. If we trigger a single wave pulse through air, water, and steel simultaneously, the results diverge immediately. The pulse crawls through the air, moves roughly 4 times faster through the water, and tears ahead through the steel. At standard temperature and pressure, sound moves through the air at 331 meters per second. In water, it hits 1,482 meters per second. In steel, it reaches 5,941 meters per second. A solid structure can transmit acoustic energy nearly 20 times faster than a gas.
To understand why, we have to look past the top-line speeds and examine the microscopic forces governing the materials themselves. Sound is a mechanical wave. This means it relies entirely on physical constituents, atoms and molecules, bumping into one another to pass the energy along in a continuous chain reaction. This distinguishes it from electromagnetic waves, like light or X-rays, which can travel freely through a perfect vacuum. If there is no physical matter, mechanical waves cannot exist. Because sound requires a medium, its speed is dictated entirely by that medium's internal personality, specifically, how stubbornly its particles resist moving, and how aggressively they snap back into place once disturbed. Acoustic energy travels as a longitudinal wave. A longitudinal wave is a wave where the particles of the medium oscillate forward and backward along the exact same axis that the wave itself is traveling. We can model this using a piston inside a long pipe filled with air molecules. When the piston is pushed inward, it forcefully shoves the adjacent molecules together. This creates a region called a compression. A compression is a localized area where particles are tightly packed, causing a temporary increase in both density and air pressure. When the piston pulls back, it leaves behind an empty space called a rarefaction. A rarefaction is a region where the density and pressure drop below their normal equilibrium levels as the molecules spread out. As the piston continues to pump, these alternating bands of high and low pressure travel down the pipe, but the air mass itself is not flowing from one end to the other, only the disturbance pattern is moving. Tracking a single particle reveals the exact mechanism. The particle merely shifts forward to bump its neighbor, then rebounds to its starting position. The overall speed of the wave depends entirely on the brief moment of interaction between these particles. It is a measure of how quickly one atom can successfully transfer its momentum to the next. What we perceive as the speed of sound is actually the physical speed limit of information transfer through a specific material's internal architecture. That speed limit is determined by an ongoing physical struggle between 2 competing properties of the medium, its elasticity and its inertia. Elasticity provides the restoring force. When a particle is pushed out of its normal position, the material's elasticity dictates how violently it snaps back. A higher restoring force accelerates the wave. Inertia, on the other hand, resists the wave. Inertia is determined by the mass density of the material. Heavier particles require more energy and time to accelerate, inherently slowing the wave down. This equation defines the bulk modulus, the standard measure of elasticity for fluids and solids. It's calculated by dividing the change in pressure by the volumetric strain. The universal wave speed equation combines these forces. The velocity of sound equals the square root of the bulk modulus divided by the mass density. Dimensional analysis confirms this relationship. Dividing a measure of pressure by a measure of density yields units of velocity squared, requiring the square root to resolve down to meters per second. We can visualize this ratio using mechanical springs and weights. If you connect masses with extremely stiff, high-tension springs, pulling one causes an almost instantaneous, violent chain reaction down the line. If you swap those out for heavier weights connected by weak, loose springs, the exact same initial pull results in a sluggish, slow-rolling wave. The ratio of stiffness to mass dictates the behavior of the system. This single equation successfully predicts the propagation of mechanical waves in any substance, from Earth's dense iron core to its thin upper atmosphere. This equation presents an immediate paradox. Since mass density sits in the denominator, a heavier material should yield a slower wave. Yet sound travels much faster in dense steel than in light air.
This table compares air, water, and steel. Steel's density is 6,000 times greater than air's, but its bulk modulus is millions of times larger. Looking at this bar chart, the massive scale becomes clear. The sheer elasticity of the solid completely dwarfs the dampening effect of its heavier mass. In a solid like steel, the interatomic bonds act like incredibly short, rigid springs. When one atom moves, the bond transmits that force to the next atom almost instantly, resulting in very high wave speeds. Liquids, like water, are much more difficult to compress than gases, giving them a high bulk modulus. Their lack of rigid crystalline bonds keeps them slower than solids, placing their sound speed squarely in the middle. In every case, the stiffness of the medium outpaces the penalty of its weight. High density only slows sound down when comparing two materials with nearly identical stiffness. Across distinct states of matter, the restoring force is the dominant mathematical factor. Sir Isaac Newton was the first to attempt a rigorous mathematical calculation for the speed of sound in air, but applying the general formula to a gas proved difficult. Newton recognized that pressure waves create temperature fluctuations. However, he assumed that sound travels slowly enough that the air's temperature has time to equalize with its surroundings. He defined this as an isothermal process. An isothermal process is a thermodynamic change where the temperature of a system remains strictly constant because heat is allowed to slowly dissipate. Under isothermal conditions, the bulk modulus of an ideal gas is exactly equal to its pressure. This led Newton to substitute pressure directly into the universal equation. Plugging in the standard atmospheric pressure of 1.013 times 10 to the 5th pascals and an air density of 1.29 kilograms per cubic meter yields a specific prediction. The math spits out a speed of exactly 280 meters per second. But the experimentally measured speed of sound in air is 331 meters per second. Newton's rigorously derived formula was off by a massive 15%. His mechanical logic was sound, but his thermodynamic assumption failed. Sound does not wait for heat to dissipate. Over a century later, the French mathematician Pierre-Simon Laplace identified the flaw. He argued that the passage of sound through air is not isothermal, but adiabatic. An adiabatic process occurs when a physical change happens so rapidly that no heat transfers. The acoustic compressions and rarefactions cycle too fast for thermal energy to escape. Trapped heat in the compressed zones forces the local pressure to spike much higher, effectively making the air stiffer and increasing its bulk modulus. To correct the math, Laplace introduced gamma. Gamma is the ratio of specific heats, a thermodynamic value that accounts for trapped thermal energy. For air, gamma is roughly 1.4. Laplace multiplied the atmospheric pressure by this ratio, finalizing the correct equation for the speed of sound in a gas. Multiplying the pressure by 1.4 increases the numerator, perfectly accounting for the added stiffness caused by the trapped heat of the passing wave. Running the numbers through Laplace's corrected formula yields a speed of 331.3 meters per second, aligning perfectly with physical observation. Newton mapped the mechanical framework linking elasticity and mass, but it took Laplace's grasp of thermodynamics to complete the picture. The speed of sound is the exact mathematical footprint of a material's internal physics. It forces us to measure both how a substance moves and how it handles the heat of that movement.